So to begin, I'm going to go ahead and let you read the CLO for the part we're going to focus on today. So today in this lesson, our CLO is that students will be able to compare in writing key features of equations using function notation, x-intercepts, and y-intercepts, and the following language: if-then statements, independent variable, dependent variable, input, output, x-intercept, y-intercept, relation function, situation, equation, table, and graph. So go ahead, in your own words, tell me what you think we're going to work on today. So I'm going to start down here. So hopefully you notice that we are comparing the key features. So making my way through the vocabulary, independent variable, dependent variable, are all over here in this vocabulary section. So I'm going to just go through each one. So independent variable. So in math, you might have been taught that variable means letter. And it's not that that's not true. It does mean letter, but really variable is something that can change. So variable, it's like to vary. Vary, it could change. So variables are things that can change. And if it's independent, something that is independent means that it exists on its own. So something that can change, but exists on its own. Another way to think about that is isn't affected by anything else. So in math, the most common independent variable that we see is known as time. Because time always passes. Nothing's going to affect time passing. Days are going to go by, minutes are going to go by. No matter what, things are going to keep going. So usually the independent variable in a situation is considered to be time. But the variables in math, things we don't know because they can always change. The reason why it's called a variable is because it can always change or vary. So we don't always know exactly what it is because it could be any number. So what we use to represent any number are usually letters, which is why variables are letters. And so the time variable, the independent variable we use is x. So x is the independent variable in math. So then dependent variable is still something that can vary, it can change, but the number is because of something else. It depends on what happens with something else. It's another way to think about it. So like if it's dependent, it's because it's depending on a different thing for it to exist. For example, in math, the big one is amount. So the dependent variable, for example, if you're representing how much money you're making, the amount of money you have definitely depends on how much time has passed, how much days have gone on, how many hours you've worked. So the amount of money you make always depends on how many hours you worked. So how many hours you work, that just is time. You're just going to work hours. But then the amount of money you make depends on that. And so that is one of the most common situations that show up in math is how much money you make depending on how much time you've spent working. So I'm going to do some more examples real fast. How much money you make is dependent on how many hours you work. So in this case, because in math, the amount, the dependence variable is known as the y. In this case, the independent variable is how much time you worked. And then, so that would be your x would be time. And then the dependent variable is the amount of money you have depends on this independent time. So then if I were to do another example, let's say how much candy you have depends on how many houses you trick or treated at. So in this case, the independence variable is the houses you went to. But then depending on how many houses you went to, the dependent variable, because it depends on this guy, is how much candy or amount of candy. You can also think how tall you are depends on how old you are. So then your height would be depending, so height would go here, and then your age is independence. So in math, you always have these two things. You have something that's dependent on an independent factor. That's usually time and amount. So then, based on these two things, we come up with the two variables, x and y. And then x and y also have two other names. The input is always your independent variable. So input's always x. And then your output depends on whatever you put in to the equation. So your output is the dependent variable, which means your output is always what letter? Y. So we will talk about this more. The input is x, output is y. So there's a few things that we're going to learn in this lesson that's more vocabulary words that I just quickly want to talk about, and then I'll explain it deeply later on. So x-intercepts, another word or way to talk about x-intercept is where the graph crosses the x-axis. It's also when y equals 0 or when you have nothing. And I will deeply talk about all of those in a little bit. And then a y-intercept is going to be where the graph crosses the y-axis when x equals 0 or at the start of time, also knowing the starting amounts. So for now, just copy these down and I will explain them all more deeply once we get to examples with them. And then same thing for relation and function. So a relation is anything that relates x and y. So anything in math that relates independent variables with dependent variables, or inputs with outputs. So what in math do you know of that have x and y in it? So in math that have x and y, we have equations, tables, graphs, and situations. So those are the four ways we model math ever. So you can model math with a real life situation. And then you take that real life situation and you model it with graphs, tables, and equations. So all these things have x and y's in them. And so they're all relations, all of these. Anytime you ever see any equation, table, graph, or situation, it's called a relation because it's relating x and y. However, functions are special relations. So functions are also equations, tables, graphs, and situations. However, they're special ones where for each input, there is only one output. So let's talk about this. We're going to talk about what a function is for all four types of relations. So in a very conceptual way, here's what's going on. Let's pretend I have a little machine. And when something goes into that machine, input, so I put something into the machine, and then something happens to it in here. Some math happens. And then out of the machine comes an answer, and our answer is also known as our output. So it says in the instruction, a function is a special relation where for each input, there is only one output. Meaning, as long as I put something in and only get one thing out, we're good. So what would be a problem is, let's say I put 3 in, and I get out an answer for some reason of 1. That's fine. But then let's say I put 3 in again, and then this time I get out an answer of -2. This is now a problem. No, this is not a function. Because to be a function, every time I put something in, I should only get one answer out. So when I put 3 in the second time, I shouldn't have gotten out a different number. I should also still get out that same 1 as the first time. Some people explain this with like a soda machine, right? So if you have a soda machine and you input the button for a Dr. Pepper, and then you press it, and then out comes a Dr. Pepper. The first time, that's great. And let's say you press it again, and the second time you get out a Sprite. This machine is broken. It doesn't make sense. Like, you shouldn't put in the same information, but then get out 2 different things. So this is also would not be a function in the soda machine situation. If I were to take a situation that's like, on day 1, I have $10. On day 3, I have $10. On day 5, I have $20. Well, remember from above, input in math is the same thing out here as the independent variable. And the independent variable in this situation is the days that have passed. So the days independent variable is the days, and the dependent variable is that amount of money. So the x is the days, and the dependent variable is the amount of money. So do I have any independent variables? Because remember, independent variables also are input that have 2 answers, because that's what would make it not a function. Let's see, day 1. So if I input day 1, I get out the answer of $10. That's my input output in that situation. On day 3, I also have $10. Then on day 5, I have $20. This one is kind of interesting because I see 2 10s right here. And so that might make people think, oh, it's not a function because the same number showed up twice. But that's not how it works. It's okay to have the same amount of money on different days. Just like up here, if I had another type of soda button, it could also say Dr. Pepper, and I could have 2 things that give me Dr. Pepper. So it is okay to have 2 different inputs, like 1 and 3, that have the exact same answer, like 10, because that's totally possible. So this is currently still a function. What makes it not a function is if I do something weird, like saying, then on day one, I have $50. How is that possible? How is it possible that on day one I have 10 here, but then later on day one I have 50? Like, that makes no sense. On the same day, I should have the same amount of money. And so because of this point, where I have two inputs, being one, that were the same, but then I had two different answers for that same thing, this is now a problem. This is not a function once I add that in there. So that's with situations. With tables, remember X is input for the independence and Y is output or the dependent variable. So if X is 1, let's say 2, and then 3, and then 2 shows up again. If, let's say 1 goes in and has an answer, whatever the machine is, it goes into the machine and has an answer of 9. And then 2 goes into the machine and it also has an answer of 9. This is okay. It is okay for two different inputs to have the exact same output, to have the exact same answer. And then let's say 3 goes in and gets out the answer of 10. Now, look, if you look, I'm putting 2 in again. I'm putting the same input in there twice. If I get out 9, like I did the first time, then this yes would be a function. Yay. However, if something got put in there that was not 9, yeah, I'm going to do it like this. Function. Then if I took the exact same table, however, when I put in 2 instead of getting out 9, let's say I got out any other number, like 3. Well, now this is not a function because 2 went in twice. I had 2 x's that were the exact same, but then I ended up with 2 different answers. So again, if I draw this in my little function machine, if a number goes in and comes out to an answer, and a different number goes in and comes out to the same answer, that's fine. This is okay. For 2 different things to go into the same answer. It's not okay for one thing to go in and then come out with 2 different answers. This is a problem. That is not a function. So then let's talk about it on a graph. So remember, on graphs, the x-axis is this dark line. And remember, axis just means line. So this is the x-axis. And it goes side to side, left and right. And then the y-axis goes up and down, and so that's the dark line for the y-axis. So then this point right in the middle is 0, 0. And so let's say I'm plotting points from my function machine. And let's say in my function machine, I put in x of 1, and I get out the answer of like 3. So then I have a point where x is 1 and y is 3 right there. So then let's say I put in 2, and I also get out 3. When my x was 2, my answer is also 3. This is okay. Remember, it's okay for different x's to have the same answer. The problem is let's say I put in 1 again. So I go over 1, but then this time I get out the answer of -1. Well, now this is not a function anymore. So what does it look like when it's not a function? If you have an x and then you go up and down and you hit more than 1 point, you have a problem. Because if you go up, there's a point, and if you go down, there's a point. That means that x of 1 has 2 answers. And if an input, an x, has 2 answers, 2 outputs, it is not a function. So if I were to take this graph of a circle, circles are definitely not functions. And here's why. If I go over to any x, like let's say even x is 1, where does x is 1 meet the graph? Well, if I go up, it meets it right here. So x is 1 has an answer all the way up here at like 1, 2, 3, 4, 5, 6. But then also it has an answer at -1, 2, 3, 4, 5 and a half. So because this x of 1 has 2 answers, it's not a function. Another way to think about it is if you can draw a straight line up and down and hit the graph more than once, so I hit it right here and right here, that is a problem. And it is no longer a function. So any x, so even like this x right here, when I go up and down, look, it hit it down here and it hits it up here. So that's a problem. Let's say I did a graph like this though. Is this one a function? What do you think? Well, if I were to pick any x, like let's go with 1, and I go up, there's no blue line, but if I go down, I find my graph is right here. So that one only hit it once. Can I draw any up and down line that hits it more than once? Remember, they have to be completely straight up and down. So this one only crossed it once right there. If I do another one, look at that one only hit it once right here. If I do another one, and actually if I move this line all the way, you see it's just hitting once right here, once up here, once up here. So as I move my straight line back and forth, everywhere it's only hitting that graph once. Therefore, this one is a function right now. Let's pretend I even at the end and took this part of the graph and went whoop. Now I have that little curly up in there. Well, if I were to take my up and down line and move it over here, suddenly I have a problem. And suddenly this is not a function anymore. Because this up and down line hits it 1 time right here, 1 time right here, and 1 time down here. Which means this x value has 3 answers. And that's a problem because each x should only have 1 answer. So now this one would not be considered a function anymore because of that little boop. That's graphs. When it comes to equations, if it says something like this one is a function, but we don't know that. At least not for sure. If we can't be positive this is a function right now because we don't know, we haven't tested plugging in every single x value to see if it will give us out more than 1 answer. And if we tried that, it honestly would take our whole life to try plugging in every single one of these. But luckily, someone else has already done it. And so someone else knows, hey, wait, this equation, it is a function. And so to let the rest of the world know that I've proved it, I'm going to, instead of calling the output y, we can call it y, but we can call it something else. And the other thing we call it is this. We read this f of x. F of x. It does not mean it's getting multiplied. It is not f times x, like a lot of us might think. What f of x means the letter in front, the F, is just the name of the function. So what this stands for, this is called function notation. Function notation. And here's what it means. If an equation is a function, it will be marked with function notation instead of y equals. So the letter, first letter, is the name of the function. So it doesn't have to be an F technically. F is most common because F for function. However, it would have been the same if I said g of x or s of x or t of x. It just means function notation. Like it's a function and this means y. They all mean y. So then for all of them, equals would go out of it. So these are all just outputs. The answer. And the first letter is the name of the function we're talking about. And the reason why they do it like this is because like if I just gave you a ton of equations, like if I was like y equals 3x minus plus 1, and then I said y equals x plus 5, and then I said y equals negative 2x, and then y equals 5x minus 1. And then if I told you plug in 3, you wouldn't know who I was talking about. Which one? Do you mean all of them? Should I plug in 3 to all of them? That's a lot of work. But if I were to name them, if I were to say, okay, this one I'm going to call F, and then this one I'm going to call G, and then this one I'm going to call S, and then this one I'm going to call T. So now, if I say plug in 3 to S, then you know which one I was talking about. I would mean this one right here. So giving them names really helps, which is why that first letter is there. The second letter, the one in the parentheses, tells you your input. So the way that this really works is f of x means the function's name is f, and we are inputting x. The one in the parentheses tells you what we're putting in the input slot. It is very normal if we have an input slot that's like this is where the thing we plug into goes, that we put an X there. It's what people like to use. But we don't have to use X. We could use any letter. So I could put an N there, and that would just put an N here. Or I could put a T here, and that would just put a T here. So again, this letter in the parentheses is just what goes in the input slot. What are we using to say input slot? Usually we use X. But what that also means is that I could do this. And what this means is for the function named S, the input is 3. So this is saying in a very short way, plug in 3 to that one. So because of that, we don't need long words to tell us what to do, because that would be the instruction. That just means for this one, for S, put 3 into that input slot. And so we'll get a lot more into this for the next lesson, but in short, this is function notation. And if function notation's on an equation, that's how we know someone else has already proved it's a function. There's no way you're going to ever have to prove it yourself. You're just going to have to recognize, we don't know, it could be, no one's proven this one. But if it has this notation, then it has been proven. And we can say, yes, that's a function. So now we've talked about what is a function in all 4 situations. We also need to introduce a key feature. Because key features happen to show up a lot, in math, and it's one of the competencies, and so we need to talk about it. So the first two key features that we need to talk about are x-intercepts and y-intercepts. So every single mathematical thing usually has these two things in them. So we can find them in situations, graphs, tables, and equations. Go ahead and take a minute and copy down this general structure. So I've zoomed in so that you're able to see these in good detail so you can copy them really good. This graph, the important part here is that this crosses X 4 tick marks over. It crosses Y 3 tick marks up. And it crosses X again over here 5 tick marks back. And then using those 3 points, you can create this little N shape for the graph. And then just copy down the rest as good as you can. Pause if you need to, because I'm going to keep talking in the video. So x-intercepts, if we scroll back to our original definition at the beginning, the first definition is about graphs. So an x-intercept is where the graph crosses the x-axis. So the reason why this is the first definition is because intercept means to cross. Like in football, if you intercept the ball, it's because you're crossing the path of the ball and grabbing it. So intercept means cross. So an x-intercept, it's where it's crossing the x-axis. Remember, axis just means line. So this is the x line right here because it goes left and right. So in our graph, our two x-intercepts, because it crosses this line twice, we have two of them. We have one right here, and then we have another one back here. So this point, remember we always write the x first, so it went right 1, 2, 3, 4, right 4, comma. However, it did not go up or down. The y is 0. Because remember, y-axis is up or down, and to get this point right here, I might have had to go right 4. But because it's on the x-axis, because it's on this line right here, this x-axis, it means it's not going up or down because it's staying on the x-axis, which means for x-intercepts, the y, the second one, is always going to be 0 because it's not going to go up or down. So for this point, the one back here, I went backwards 1, 2, 3, 4, 5. So I went left 5, so that's -5 for x, but then my y was 0 because it does not go up or down. Which means anywhere on this line, if it's an x-intercept, y is always 0. So that's our second definition for x-intercepts. Is that for the x-intercept, y will always be 0. So we can use that in a table, for example. So when we look in the y column and find where y is 0, it's right here. And this is the type of table where the point goes side by side. So for this one, my x-intercept would be 1, 0. So if y is 0, so if we move to our situation, so if y is 0, y in a situation is our dependent variable, or our amount. And the amount, in this case, is the amount of money, because it's about days and how much money you have. So in this case, so when the amount is 0. So if I read this, day 0, I have 25. Day 1, I have 20. Day 3, I have 10. On day 5, I have 0. So that's going to be my x-intercept. That on day 5, I had nothing. And then finally, in an equation, if I want to figure out the x-intercept, I'm going to use the whole y is 0 thing. So I'm going to plug 0 into y and solve for x. So this is one of the times that the last unit gets brought up again, because it will keep getting brought up again and again. So I'm going to take this y and I'm going to make it be 0, because it's an x-intercept. And then I'm going to write the rest of the equation down. And I'm going to go ahead and solve it for x. So my first step is to do what? I need to add 1. And that means I have to do it on this side of the equal sign as well. And so 0 plus 1 becomes 1 equals 4x, because these two cancel each other out. Now how do I get rid of the 4? We divide. So then if I divide this side by 4, and I have to divide this side by 4, my 2 4s on this side cancel. So that 1/4 equals the x, because these 2 4s went away. And so finally, my x-intercept is that when x is 1/4, y is 0. And I know this y is 0 because I put 0 into y, into that equation. All right, so that's x-intercepts. I'm going to do y-intercepts here in a second, but quickly, for all of these, you should be able to tell me whether or not it's a function. So, just to quickly test your memory, for this graph, is it a function? Yes, it is, because every up and down line that I draw would only cross it one time. For this table, is it a function? No, it's not, because down here I have 1 being 0, and I have 1 being negative, equaling -2. And that's a problem, because I can't have two x's that have different answers. So this one's not a function. Is my situation a function? Yes, it is. There is no day that repeats like day 0 again with a different amount of money. So this makes complete sense. It's a complete function. Is this equation a function? Actually, we don't know on this one, trick question, because it could be a function. We just don't know because they put y instead of function notation, which would tell us for sure if it was a function. All right, jumping back down to y-intercepts for all these. So if x-intercepts are where the graph crosses x, what are y-intercepts? Where the graph crosses the y-axis. So if I go up to my little graph, y is up and down. Where does it cross this dark up and down axis? Right here. What is this point? Well, remember, we always write the x value first. So for this point, did I go left or right? I did not. That means my x is going to be 0, because I did not go left or right to plot this point from the middle. I only went up 3, and up is the y value. So in the same way as the other one, if I'm only going up and down for the y-axis, because it's not leaving this line, this axis, that means I am not ever going to go left or right if it's a y-intercept, which means for y-intercepts, x is always 0, because I'm never going to go left or right. I'm only going to go up and down. So if I go to my table and I find where x is 0, oh, that's right here. So my y-intercept is going to be 0, 2. That's for this table. X being 0 in a situation. Remember, in a situation, x is our independent variable. And the most independent thing in math is time. And in this situation, it is talking about days. So if the day is 0, that is the starting amount. Because on day 0, that means before any days have passed. It's like how much you start with. So y-intercepts are the starting amounts, or how much on day 0, meaning no days have passed. So in our situation up here, it said on day 0, I had 25. So my y-intercept would be 0, 25. And then for the equation, if x is equaling 0, then we're going to plug in 0 for x and solve for y. So if I go up to the equation, it was y equals 4x minus 1. But in this case, to figure out what my y-intercept I'm gonna plug in 0 for x. So instead of x, I'm gonna put 0. So then y equals 4 times 0 is 0 minus 1. So y equals 0 minus 1 is negative 1. And now that I've solved for y, I know that my x-intercept was that when x was 0, my output was negative 1.